Today I'm going to talk about something that I struggled to pinpoint during my research on the foundations of physics. What it means to be mathematically precise, at least the modern standard. Things have been evolving through the centuries. We'll see how mathematical precision is slightly different from what one needs in physics or philosophy and so on. Now, this has always been a very practical issue for me, not a philosophical one. I'd prepare something, ask feedback from a mathematician, and he'd complain. It's not precise. And I go back and change it, and again, it's not precise. And this was particularly frustrating because nobody would tell me what exactly was not precise. I think that most mathematicians actually don't consciously know. They do it, they can recognize it, in the same way you can speak a language fluently but not be aware of all the rules. The other thing that bothered me is that I had done enough software engineering to know how to be precise in that context. Software design, in the end, when it's done well, means essentially constructing a correct and precise formal system. If it's not correct and precise, the software is not going to do what you want it to do. And depending what you're doing, it's a loss of time, money, life, and possibly all three. So it's important to be precise. It has consequences. You have to think about all possible error paths, account for each of them, so if the system fails in a controlled way. In a way, you have to prove to yourself the program is correct. Unfortunately, most people don't do this. They simply keep writing code at random until it seems to do what they want it to do, and that's why we have so much crappy software nowadays. But the point is, it's not that I couldn't be precise, it's just I didn't know what it meant in the context of mathematics. I struggled with this for many years. Then I had the good fortune to talk about this to a mathematician who I met at a conference. And after looking at some things I wrote, he also said I had to be more precise. So I told him plainly what I understood of the situation. I said, look, any formal system will have to start from some elements that are left undefined. You're going to have some axioms, and those cannot be defined further. If you do, it's simply in terms of other axioms, and you're not really solving the problem. So for example, in Euclidean geometry, you have points, lines, and those cannot be defined further than that. You have them, you know intuitively what they are, but that's it. You can't be more precise than that. And he said something very interesting. He said, you're absolutely right. And he said, but the only thing you're allowed to leave undefined are the elements of a set. That is the convention. So finally, somebody gave me clear instruction, a clear specification. So I was able to rewrite the things I had to that effect, and I had no problems after that. So let me tell you exactly what that means. Let's see what my exact problem was and what it means, what are the ramifications of all of this in terms of relationship between mathematics and physics. So the most fundamental objects in our framework, in my research, are statements. In particular, verifiable statements. Things like the sky is blue and that animal is a cat, or the temperature of the oven is between 300 and 310 Celsius. Things you can say about the world that you can confirm experimentally. In my work, a scientific theory is essentially a collection of such statements, and the mathematics is used to keep track of the relationship between the statements. If this animal is a cat, then this animal is a dog must be false. If velocity at time t is such and such, then the position at time t plus dt is such and such. Now, it is very important that those statements are taken as a unit. That is, I don't want to formally define what language of grammar they use. I don't want to formally define their meaning. I don't want to formally define how you test them. There's a lot of reasons why you shouldn't try. The gist is that it doesn't work, and we can talk about this some other time. The point is that I have to leave the notion of statements as prime undefined, like the points and lines of Euclidean geometry. We have these things, we intuitively know what they are, they follow these rules, and that's it. To make this even more concrete, my earlier definition were things like a statement is an assertion that is either true or false. And then I had a set S of all statements. Now, to me that was precise. If I have an object, I can look at it and determine whether it is a statement or not. An apple is not a statement. A poem is not a statement. The sky is blue is a statement. Then I'd say something like, given a statement, I can find the negation, which is the statement that must be false when the first one is true, and vice versa. And I'd reasoned to why that was the case to convince myself that was true, that I had such thing called a negation. But to a mathematician, this is not precise. At least not today. Hundreds of years ago, people were doing things like that in math, but not anymore. Nowadays, what I had was not precise. So why? Well, take identification. For example, an apple is not a statement. This is not happening formally. It's done intuitively. It's outside of the formal system. You can't write a proof for it. You can just say, well, it's obvious. An apple is not an assertion. You're not really proving this from your starting points in a formal way, so it's imprecise to a mathematician. So how do you make things formally precise? The formal definition I have now reads something like, formally, a logical context is a set, a collection, whose elements are called statements. That is, I have a set, the logical context, and I call the elements of that set statements. And that's it. I say nothing about what they are. Technically, they're just symbols, and you don't care what they represent. And this is now mathematically precise, because what I left undefined are the elements of a set, and because I said nothing about them. So there is nothing informally specified. Then on top of that, you can add other formal properties to your objects. You say the logical context comes equipped with a function negation that for each statement gives you another one, and you give the property of that function and so on. But you don't try to derive those properties from the original informal idea of a statement. You simply impose them. So what is happening is subtle, but is very important. The way that I made the framework formally precise is not by specifying everything formally. It's by removing all that I couldn't specify formally. Maybe counterintuitively, what you have is something that is both more general and more precise. It is more precise because, as we said, we only talk about formal definitions, things that can be totally expressed by symbols on a piece of paper. It is more general because anything that fits those formal definitions can be described by the framework. For example, you can find that spatial velocity and scalar function both satisfy a similar formal structure. They both have an addition, they have a scalar modification, they both form vector spaces. And what you can prove for vector spaces in general now applies to both cases. And this is a win-win for math. It's very powerful and beautiful and insightful, but ultimately it's not necessarily a good thing for science, philosophy, engineering. And let's see why. First, since our symbols can represent anything that fits the formal structure, we do not know what the formal structure is talking about. We're talking about statements, bananas, horror movies. Formally, it does not matter, as long as you have operations that have the same property. But when you're doing physics, it does matter. How do you perform experimental tests if you don't even know what your objects are? And this is not some abstract problem, it's an actual problem. The whole issues of interpretation of a theory happens when we start with a formal structure and you try to reconstruct the informal part. And you can't do this uniquely. Effectively, your theory is incomplete. You literally don't know what you're talking about. Without the informal part, you don't have a well-specified physical theory. You may be formally precise, but you're not scientifically precise because you don't know how to match all the elements of your theory to experimental verification. The second problem is that formal systems cannot tell you whether you have the right starting points, only if those are consistent. You can impose whatever structure you want. You can say that each statement has two negations or that it does not have a negation. You can have determinism, reversible evolution, one-to-one maps in times, and things like time loops, and therefore something existing multiple times at the same time. You can create systems that are formally precise, but they're not conceptually precise, not conceptually consistent. Again, these are not problems to a mathematician. Mathematics is a game played according to certain simple rules with meaningless mark on paper. This is from David Hilbert. Remember that I said we have to start from axiom? Well, Bertrand Russell says this. It is essential not to discuss whether the first proposition is really true, and not to mention what the anything is of which it is supposed to be true. So the idea is mathematics has become the meaningless manipulation of symbols is not a weird view, it's a very common view in mathematics. It's like mathematics knows the rules for everything but the meaning of nothing. So while mathematical precision is very nice, it is not the beginning and end of all things. It's not the only type of precision we should care about. There is no hierarchy where math is more precise than science or science is more precise than engineering. This is just nonsense. We need to be mathematically precise to know exactly what depends on what. That covers only the formal part of the system. We need to be scientifically precise so that we know how to map the formal system to the physical reality, to experimentation. And that can only be done informally. And we need to be conceptually, let's say philosophically precise, so that our informal system is consistent with itself and with the formal system. So how the heck do we do it? So here's how I do it. This is the standard I came up with because I didn't really see something that was doing it well. Maybe somebody can do it better, but this is how I do it. So for example, this is an axiom I currently have. A statement is an assertion that is either true or false. A logical context S is a collection of statements with well-defined logical relationships. Formally, a logical context S is a collection of elements called statement, upon which is defined a function, truth, from the logical context to the Boolean set containing true or false. So we have two parts. The first part of the definition is the informal definition, the intuitive one, that says what we are actually talking about. An assertion that is either true or false. Then we say formally and give the formal definition. It clearly states what is captured by the formal system. A set of elements, elements are undefined, and that's it. For some axiom and definition, those are not completely obvious, we have a justification. This is not a formal proof because it's part of the informal system. It's an argument that says, look, if we said that these symbols represent these actual concepts, then they must also have these properties. Those are the kind of informal arguments we can follow with our intuition. In a way, they are the most delicate and important arguments we have, because if we botch those justifications, we will have a very nice formal system with nice theorem that have nothing to do with reality, with the reality that we want to describe. So I differentiate, for example, between axioms and definitions. Axioms bring in new concepts within the formal system. Definitions specialize concepts that are already present in the formal system, that are already axiomatized. So the idea is that we define statements in an axiom because we're bringing in these new objects. But the idea that, for example, one statement is independent from another, that the truth of one does not influence the truth of the other, is a definition because you're just giving a name to a relationship between objects that have already been introduced, that have already been formalized. You still may want to justify the definition to show that the intuitive sense is being captured correctly, but you are not introducing new objects. And the game is the following. You want to have the least number of axioms as possible. You want axioms to be very simple with a very straightforward justification. They should be conceptually simple with a simple map between formal concept and physical concept. The reason is that you want to push as much as possible, as early as possible in the formal system. That is where you're guaranteed to make fewer mistakes. So the surface exposed to doubt is much smaller. You can have as many definitions as you want, but you have similar trade-offs. You want to have definitions that map well to intuitive concepts, that are formally compact, that map well to current mathematical definitions so that we're not directly recreating all sort of different stuff that is not known, and that can be used to prove interesting things. And that's where the game becomes most interesting to me and most satisfying. In fact, most of the game is trying out different definitions, see how they work, trying to write proofs to see if the definition don't quite work, realizing that they don't work because you're not capturing some actual physical concept, and so on. And you win when the structure you have is obvious. You go to someone else and he says, oh yeah, well, naturally you'd have that, and he goes away. Good math, like good physics explanation, like good engineering, you know they're good because they're simple and obvious. And you don't realize how awfully complicated it was to get there. So that's more or less what I wanted to say about mathematical precision. So let me sum it up. Mathematics only deals with formal systems and formal properties. Mathematically precise really means formally precise. There is nothing that is informal. Everything is inside the formal system. Therefore, it can only describe the parts of the words that can be captured by a formal system. It does so not by making everything formal, but by ignoring all that is informal. In current practice, the only thing you can leave undefined are the elements of a set. And those must be left fully undefined in your axioms. So it's better to think about mathematical objects as symbols that represent things instead of the actual thing. Now, this level of precision is insufficient for science. We need to be scientifically precise, meaning we have to know how the symbols map to the physical objects, or we cannot proceed with experimental verification. We need to be conceptually or philosophically precise to make sure that the informal system is consistent and inconsistent with the formal system, that the formal system is capturing the properties of the physical objects correctly. Note that all these types of precision cannot be added on top. You have to build them into the framework from the beginning and always make sure you don't break them. Big conceptual frameworks that are precise do not come from big conceptual frameworks that are not precise. They only come from small conceptual frameworks that are precise. The idea that you can take a formal system and sprinkle on top an interpretation to make it more physically precise, it just doesn't work. You have to start from the most basic structure, and that's what we found out, and that's what we're doing in our project, Assumptions of Physics.